So the key thing to remember is the notation we use for a previous term. Because for any number in the Fibonacci sequence, let's say 8, well, how do we come up with 8? We add the previous two numbers, right? Okay. So if this was our nth term, this would be our n minus 1th term, right? And this would be our n minus 2th term. There you go. So in order to get the nth term, you got to add the previous two. So you would add a sub n minus 1 plus a sub n minus 2. That just means like 2 terms ago. Because you remember on Tuesday I said that this a sub n minus 1 just means previous term. Whatever. And then so it's a sub n minus 2, which means like 2 terms ago. This Fibonacci sequence, hopefully you guys found it kind of interesting. You guys enjoy the video at least somewhat, as much as you can enjoy school while you're at home. So this guy, I want to talk a little bit more about him, Leonardo Fibonacci. His last name actually wasn't Fibonacci. It was something that kind of got added on in the 1800s. He is also known as Leonardo of Pisa, or Pisa, however you want to pronounce that. He was born in Pisa, Italy, and famous for of course, the Leaning Tower there in Pisa. And I was kind of interested to see like if he was actually around while they were building this thing. And it turns out that's a pretty good timeline. He was around this Leaning Tower of Pisa. They started building it in the year 1173, and he was born in 1170, so they started building it when he was about 3 years old. He died in 1240 to 1250, we're not really sure. That's about when he died. This Leaning Tower, though, if you've ever looked it up, it's kind of interesting. It took several hundred years to actually finish it. They finished it in 1399, so much later. The reason why is because they stopped a few times because it was leaning so much that they stopped construction. And the reason why it leans is Pisa, Italy is, I think Pisa actually means marshland. And so the ground underneath this is so wet that it was just the foundation's kind of sagging in. And they tried to correct it, and they were never able to get it right. So they eventually just kept building it up. Again, they tried to correct it, I think, by making this side dimensions a little bit smaller and then keeping this one higher, but it keeps sinking, and it still continues to sink more and more. Every year it leans more, a little bit more. But it was meant to be like a clock tower for this cathedral. And so anyhow, that's kind of what city's famous for, the Leaning Tower, and also Leonardo Fibonacci. And he's actually probably one of the most important mathematicians that you'll ever learn about. Primarily because, not necessarily because of the Fibonacci sequence, which is important, but he started using what's called the Arabic numbering system. So prior to him, most people that did math were Greeks, right? Or the Greek mathematicians. And so they used Roman numerals because, well, it was the culture in the Greece area. Rome was close to, Greece and all that stuff. That was all kind of Greece there. And so imagine instead of writing 32, let's say, all right, like that, you instead have to write, let's see, x, 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 I. Right? So you'd have to write that every time you write 32, right? And if you get into the hundreds, even more, or instead of writing, let's say, 7, right? You gotta write I, right? I guess that'd be 8, sorry. 7 would be VII. But anyhow, you get the point. Roman numerals, you gotta write a lot more. It's not as simple as just writing these. This is the Arabic numbering system. Also, there's no 0 in Roman numerals. And so in order to get to 0, you have to have the Arabic numbering system. So he kind of adopted that and then wrote some math textbooks that used it. He also developed the concept of square roots, lots of other math word problems. And the one math word problem that gave the Fibonacci sequence was that rabbit problem. Didn't talk about that in the video. Remember, the rabbit problem. Okay. So he basically had this problem about how many rabbits there would be. Here it is here. So this is a problem written in his book. A certain man puts a pair of rabbits in a place surrounded on all sides by a wall. So this rabbit in a cage, pair of rabbits. How many pairs of rabbits can be produced from that pair in a year if it is supposed that every month each pair begets a new pair, from which from the second month on becomes productive. The idea is two rabbits, they're a pair, they create another rabbit, and then the second month later, that rabbit can pair up with another one, they create a pair, and then basically how many rabbits do you have in a year? Rabbits reproduce a lot, so that was a problem, and that actually is the Fibonacci sequence is the answer to that question. So, kind of a fascinating problem. And yeah, I think that's about it. He's so really famous. They're not really sure when he died. His dad also has kind of a cool name too. I don't know about his mom, but his dad's name was Guglielmo, which I think is pretty cool name, right? So that's how you pronounce it, right? Guglielmo.
Can I see if that's the correct pronunciation?
Oh, it's Mr. Beast.
Sure. It's probably not that, but I think it's
Bro, enter for
Guglielmo. It's an Italian word, so I don't
No. Where is it?
know. Guglielmo. Yeah. Guglielmo. That's it. Guglielmo. Alright. Alright. Guglielmo. That's still pretty cool. I like Guglielmo better. Alright, so that's Leonardo Fibonacci, one of the most famous mathematicians, mostly for the Fibonacci sequence. Actually, I have this kind of a friend of mine. This guy goes to my church, and he built a barn. And in the second story of the barn, he put in his own wood floor. And I went there one time, and he asked me to identify like the pattern on the floor. And he had like two different shades of wood, and it was in the Fibonacci sequence. So he's kind of a math geek. It's kind of neat. So today we're going to still talk about sequences. Not necessarily the Fibonacci sequence, but we're still going to talk about sequences. And we're going to expand on it a little bit and do something called a summation. Okay. The summation is still a sequence. It's just sort of an additional thing we're going to add on to these sequences. And we're still actually in the same section. Kind of a lot here. So we're going to find sums of sequences. So question first, just like the other day we had that exclamation point, right? And that was called a factorial. Anybody know what this here is?
Wait, no.
Huh? Huh? You've seen it? That's close. That's a good guess. Delta. Yeah, this is a sigma. It's the Greek letter sigma. Yeah. Someplace you might have seen this, like sometimes like sororities and fraternities use Greek letters, right? But yeah, this is actually comes from math mostly. Is what it's used. But it is a Greek letter. This is the Greek letter sigma. And it's used in math a lot. It's math uses a lot of Greek letters, like pi is a Greek letter. Many other ones, theta, lots and lots of Greek letters. You just add more the higher you go in math. So here's a new one that we get to use in math. It's called sigma. And this is actually the same as the English. So if you translate this in English, it's just actually S in the English alphabet. So it's kind of looks like an E, but it actually represents S in the English alphabet. Sigma. And this is the capital letter. All right, well, how we're going to use this is in something called summation notation. Since this actually means S, why we choose S is because we're going to do sums. Okay? So this is going to be used in what's called a summation. And again, we use that because it's supposed to be the S, so it makes it to be sum. If you if you take calculus next year or whatever, or 2 years from now, you'll see a symbol that looks kind of like this. It looks like this, and it's called an integral symbol, and it actually is kind of just a stretched S as well, and that means like a summation as well. If you ever take calculus, you'll do that. It's an integral. It means kind of the same thing. All right, so we're going to talk about summation notation, which features this Greek letter sigma. So it's also called sigma notation. I might call it that. Another math might refer to it as sigma notation instead of summation notation. Sigma is a little bit shorter, and that's the letter that it actually is. So. Sigma notation is very common. All right, and what this sigma does, okay, so sigma, how I normally draw it, I don't like go through sort of a fancy way of like this each time. You can do that if you're a good artist. You don't need time. But what I normally do is just kind of go like this, and just typically how a mathematician would write it, just going to go like this, and then just. So however you want to draw it, if you want to try to make it look like that, go for it, or just do it that way. And what this sign tells you is it tells you to sum up the terms. Okay, so it's a sum. Tells us we're going to sum up all the terms in the sequence, and it looks like this. We're going to throw some more letters and numbers on it as well. Right. So here we got our sigma. Right, and we just want to write out this way. Right. And we're going to say from a letter, it won't always be k. K equals 1 to some other number. But right now we're just going to call it n. So the way we read that is the sum from k equals 1 to n. If you were to read this out loud, you would say the sum from k equals 1 to n. And then we have some, this is just going to be a sequence, actually just sort of like a function right there. This bottom part here, this tells us where we're going to start. Okay. This is like our starting term. Starting index is what it's commonly referred to. Starting index or term or index. So we're going to start with plugging 1 into this sequence. Let's say it won't always be 1; it can change. And then we're going to plug in every number up until we get to this one. So this is going to be like our ending index, our ending term. So we start here. We start at 1, then we're going to do the plug in 2, and then 3, and then 4, and then 5, and then 6, all the way up to whatever this n is. And then how we sort of write this out is you plug 1 in for k, so you would say a sub 1. The summation means we add it together. We sum them up. So a sub 1 plus a sub 2 plus a sub 3 plus ... all the way up to a sub n. So we sum up every term from the first term all the way up to whatever one it tells us to stop. Sometimes it won't be the first term though. Maybe we want to just find like the middle 8 terms of the Fibonacci sequence, or I don't know, the 3rd to the 11th term or something like that for the Fibonacci sequence. There is applications of this which we'll look at the next few days, like why would we want to do this? There is things that this is used for. Alright, so it means the sum, the terms in a sequence. Well, let's look at an example of that. So first one here, we've got the sum from k equals 1 to 5. So the sum from k equals 1 to 5 of 3k. So we start at 1, we end at 5, and this is our function or our sequence there, 3k. So we're just going to plug in 1. We do 3 times 1. And generally you write them in parentheses. There's a lot of parentheses for this one, but put each term in a parenthesis. So 3 times 1, and then plus, because it's a summation, plug in 2. 3 times 2. Because in any sequence, you always just add 1 integer each time. Right? Plus 3 times 3, plus 3 times 4, plus 3 times 5. And at 5 because that's what our top index is there. And then we're just going to be solving this and add them up. So this is 3 plus 6 plus 9 plus 12 plus 15. And what does that equal? Is that math? Uh-huh. So that's the basic gist of what we're going to be doing today. We're going to change up the indexes a little bit. Some of these. Here, this one, we're going to use an I instead of a K, but it works the same way. The number that's used for the index, or the letter, sorry, and for the index will always be the same as the one that's in there. So if that's a K, then that's a K. If this is an I, then this will be an I. If it's not the same, there's some sort of a typo or something, most likely, or you can't do it. It has to be the same letter that you're substituting in. Okay. So this one we're actually going to start with 0. It's kind of common as well. So all you're going to do is just start with the 0 cubed. 0 cubed plus 1 plus 1 cubed plus 1 plus 2 cubed plus 1 plus 3 cubed plus 1 plus 4 cubed plus 1 plus 5 cubed plus 1 plus 6 cubed plus 1. And the easiest thing to do with this one is to just plug it into your calculator from here. I would just plug this whole thing in. Do 0 cubed plus 1 plus 1 cubed plus 1. Just make sure you're doing each one in parentheses just like you have it written. Cubed plus 1 cubed 1. You can type numbers into a calculator and you can do this one pretty well. Anybody got an answer? Yeah, I did. Well, it's not that much writing. Alright, let's try a couple more. This one has a different starting index, you'll see here. So this one is going to be the sum from I equals 4 to 8. It's still the same thing, it's just instead of plugging in 1 or 0 to start, we're going to plug in 4 to start. So we're going to do 4, plug in 5, plug in 6, plug in 7, and then plug in 8 and stop 1 for plug in 8. And actually, this should be a P. I changed it, but it didn't change. Sometimes it doesn't change in my slideshow, but they actually should be a P. Sometimes they'll change on yours, but not mine here. Alright, so it should be P equals 4 because we got P's in there. So we're going to do 4 squared minus 2 times 4 plus 5 squared minus 2 times 5 plus 6 squared 2 times 6. Get the idea. Plus 7 squared plus 7 plus 8 squared plus 2 times 8. And we'll plug it in. If you want to take shortcuts as you go, you could just say 16 minus 8 plus 25 minus 10. 56 minus 12 percent plus. Big number down. See that line? I got. See that? All right, one more. This one just has one additional thing, which you'll see on some of the problems that you're going to do, and that is sometimes you'll multiply your sum. So this one just has a 3 in front of it. Doesn't change anything that you actually do. You're just going to compute this as before, the summation, and then multiply it by 3 at the end. Okay. So sometimes people want to miss them just because they're forgetting to multiply. Not a big deal. Just make sure you multiply your answer by 3. Don't like bring it into there or anything. Just multiply by 3 at the end. This one starts at 2 and ends at 7. Also, just be careful with like negatives. This is not the same as negative d squared. It's not equivalent. The negative is applied after you square it. So you actually really want to type it in as negative 2 squared, no parentheses in that part, plus 3. So we start at 2 and we go up to 7 plus negative 3 squared plus 3 plus 4 squared 3 plus negative 5 squared plus 3 plus 6 squared plus 3 plus negative 7 squared. All right, and then we need to multiply this all by 3 as well. So you could even just use brackets around it. 3, multiply the whole thing by 3. You get your answer. And it's okay to get a negative number for your answer as well. Got 3 times negative 121 and negative 363. Sum doesn't have to be opposite. So you got that? So your assignment for this is going to be some of these problems. I gave you 10 chances, so like if you make a little mistake, you can still correct it. You got not too many of them. You should be able to get them done. Of ones like we just did. There we go. So ones just like we just did. There is a couple where you have to try to write your own. Try your best on these. If you can't end up figuring it out, it's okay. But you have to try to write your own summation with the given pattern that they got here. So see if you can do that. I can help you if you get stuck. But try to do that. There's just 2 of those. Try them on your own.